In this recording, we will review the kinematic equations in one dimension. So I'm going to share a PowerPoint presentation that will allow us to see how we use the kinematic equations. Kinematic equations in one dimension. Kinematics deals with the concepts that are needed to describe motion. The first concept is the definition of average speed, which is the distance traveled divided by the time required to cover the distance. The important thing to note here is that speed is a scalar. And by scalar, we mean that we're not considering the direction. So average speed then is simply the total distance traveled divided by the elapsed time. Because distance is measured in meters and time is measured in seconds, the SI units for speed is meters per second. The first example is where we're going to calculate how far does Julian run in 1.5 hours if his average speed is 2.2 meters per second. So that means then that we will have to take our equation that we write as distance, and in this case, we're going to use the symbol x representing the distance along the x-axis divided by time. So what I'd like for you to do is always draw a chart to write down what is given in the equation. So we're given 1.5 hours. That is my time. My average speed is given as 2.22 meters per second. And we're asked to find the distance. So clearly, if we have an equation that says speed equals distance over time, to solve for the distance, in this case, distance was represented by the variable x. Then x, of course, is going to be speed times time. Now, it's important to know what will be the unit that we're finding our distance in so that we can make the appropriate changes if necessary. Or in this case, we need to first change our time into seconds because we have our speed in meters per second. In other words, when we get ready to solve for the distance and we have 2.22 meters per second, we need to have our time in seconds so the seconds will cancel out and my final value will be in meters. So of course, we know how to convert 1.5 hours into seconds. Let me go up here. We have 1.5 hours. And we know that 1 hour is 3,600 seconds. So when that cancels out and we multiply 1.5 times 3,600, that's where we get the 5,400 seconds. Then when the seconds and seconds cancel, then my answer will be in meters. Now, if you put this number in your calculator, you have 2.22 times 5400. The number you see in your calculator is actually, write this number down, 11,988. Now, the reason why we're not going to write that answer is because that answer has 5 significant digits. But if we look at what is given in the problem, we have 2 sig figs in 1.5. We have 3 in 2.22. That means that the answer can only have 2 significant digits. We go with the smallest number of sig figs in the given. So therefore, we have to round this number up and only have 2 significant digits. And that's why our answer is 1,200 meters. What is average velocity? Average velocity is the displacement divided by the elapsed time. We use the same symbol, but in this case, often you will see an arrow to designate the velocity vector, because velocity is a vector. Displacement is also a vector, so we put an arrow on top. And of course, time is a scalar. The units are still meters per second. In this example, we're given, it say Andy Green in the car thrust SSC set a world record of 341.1 meters per second in 1997. To establish such a record, the driver makes 2 runs through the course, 1 in each direction, to nullify wind effects. From the data, determine the average velocity for each run. So, as you can see in figure A, because he is moving from left to right, the displacement vector is a positive 1,609 meters. But in figure B, he's moving from right to left. And when we move from right to left, or in this case toward, in this picture, the west, then my displacement vector is negative 1,609 meters. So it's important then that for velocity, we have to indicate the direction of the displacement vector. So when I do the math here, when I solve for the velocity, moving toward the right, the velocity vector is positive. But moving toward the left, the velocity vector is negative. The notion of acceleration emerges when a change in velocity is combined with the time during which the change occurs. So now we have another equation. We call it acceleration, which is simply the change in velocity over time. For our purposes, we define change in velocity as the final velocity, written as v subscript f, minus the initial velocity, v subscript I, over time. So this equation is very easy to remember. Change in velocity over time. So our definition of average velocity is simply that, where we find the average velocity by dividing the change in velocity over time. In this example, we have the initial velocity is 0 meters per second. The object changes its speed from 0 meters per second to 260 kilometers per hour in a time of 29 seconds. So to compute the acceleration, in this case, the average acceleration, that's why we have this bar on top of our vector, an arrow for vector. We simply take the final velocity minus the initial velocity and divide by the elapsed time. Now, in this case, you notice that we have mixed units. Sometimes when we're discussing objects like a moving airplane or a moving car, it can be given in units of so many meters per hour, kilometers per hour per second. However, the SI unit for acceleration is meters per second, which is meters per second squared. So we look back at our definition of velocity, acceleration, change in velocity. That means we have meters per second divided by seconds. And the SI unit then becomes meters per second squared. That is the SI unit for acceleration. Now, what does it mean when we have the average acceleration per unit time? In this case, what it means is that the car is increasing its velocity 90 kilometers per hour every second. So initially it is at rest, but after 1 second has elapsed, it is now moving at 9 kilometers. Did I say 90? I'm going to say 9. I'm sorry, that's 9 kilometers per hour every second. So after 1 second has elapsed, it is now moving at 9 kilometers per hour. Then if I wait 2 seconds to observe its speed, now it is moving at 18 kilometers per hour. If I were to speed up even more for a time of 3 seconds, then I would add 9 more. So that would give me what? 27 kilometers per hour. That would be the speed after 3 seconds. So that means that every second, the speed will increase 90 kilometers per hour every second. Okay. Now, in this case, initially, the object was moving at 28 meters per second. So let's see what's given in this problem. Clearly, we can see that the final speed is 13 meters per second. The initial speed, 28 meters per second. And this took place when the time changed over a period of 12 minus 9. So that's a period, the time difference. You notice here that it gave us initially at 9 seconds, the speed was 28 meters per second, but 12 seconds later, the speed was 13 meters per second. So now we have to find the change in time, t final minus t initial. When we solve this problem, we notice then that the acceleration is negative. Now, the negative acceleration, we sometimes call that deceleration. It simply means that the object is slowing down. And clearly, it has to be slowing down because the final speed is less than the initial speed. So that tells me also that my velocity vector is acting in the opposite direction of motion. In other words, the object was moving at 28 meters per second in a positive x direction, but the velocity vector is slowing it down. Therefore, the velocity vector, forgive me, acceleration vector is moving in the opposite direction. Otherwise, it wouldn't slow it down. So that's what's happening in this picture. The acceleration vector, as we can see, is opposing motion. That's called deceleration. So initially, the car was moving at 28 meters per second. It's decelerating at 5 meters per second every second. Therefore, after 1 second has elapsed, it is now moving at 23 meters per second. After 2 seconds has elapsed, it will be moving at what, 18 meters per second. If I kept watching, observing the motion, if it's decelerated at 5 meters per second squared, after another second, after 3 seconds, it will be moving then at what, 13 meters per second. Here we have our 5 kinematic variables. So I can move this out of the way. The 5 variables are the displacement vector, acceleration, final velocity at time t, initial velocity, that means the velocity it has at the beginning of the problem, and the elapsed time. With these 5 kinematic variables, we can write the 5 kinematic equations. Now here the author only has 4, but actually there's a 5th one, especially for those of you who will be going into med school. You would need to know that there's also an equation where if we know the final velocity, v sub f times time, it is minus 1/2 a t squared. Now, the reason why you want to be able to have these equations and to know these 5 variables is because one of the easiest way to solve these problems is to write down what is given and then decide which of the 5 kinematic equations is best suited to solve the problem based on what is given in the problem. The reasoning here is very straightforward. Sometimes it is necessary to make a drawing so you can kind of visualize what the problem is asking you to do. Then always decide which directions are to be called positive and negative. This is very important. So our convention is that anything that moves to the right is positive. Anything that moves up is positive. If it's moving to the left, it's negative. If it's moving down, it's negative. Or we may say to the east is positive, to the north is positive. To the west is negative, to the south is negative. To the right is positive, to the left is negative. So we have to always make sure that we give the proper sign to whatever that quantity is that we are evaluating. Verify that the information contains values for at least 3 of the 5 kinematic variables. If you only have 2 identified, that means you must look closely in the problem for the 3rd one. The 3rd one may probably be in words. For example, it may say the object starts from rest. That means V initial is 0. Or the object comes to rest. That means that the final velocity is 0. Or it may say the object reaches its maximum height. When the object reaches the maximum height, at that point, the final velocity is 0. This is an example where, again, you're given the displacement, the acceleration, which of course is negative, means the object must be either, if it's on the XY axis, the acceleration is moving in the negative X direction, which is opposing motion. You're looking for the final velocity when you're given the initial velocity. In this example, you notice clearly that the time is not given. There's no information given about the time. Then that tells us which of the kinematic equations that we have to use. So if we look here, we notice that equation. 1 has time, 2 has time, 4 and 5 has time. So I must use what I'm given. I'm not given time, and therefore I choose the equation that does not require me to know time. Once I find the equation, then the equation itself has to be rearranged to solve for the unknown. Before you plug in any variables, make sure that the equation is rearranged to solve for the unknown variable. In this case, I'm looking for the final velocity. So I simply take the square root of the quantities on the right side. But what if in this problem I knew the final velocity and I was asked to find any of the other variables? So I was asked to find the acceleration. So from this equation, then, that means that I would have to rearrange it to solve for the acceleration. Of course, I write my notation a little differently. So I have v final squared. This needs to move to the other side. And of course, if it's positive on the right side of the equality symbol, on the left side, I will be subtracting it. It will be negative. So that would be 2ax. If I'm looking for acceleration, that would mean that on both sides, I'm going to divide by 2x. So if I'm looking for the acceleration vector, then I have to isolate the a. And my equation would say a equals v final squared minus v initial squared all over 2x. So now you know this value, I encourage you to solve this again and see that you get this answer for A. Our next concept is freely falling bodies. In the absence of air resistance, it is found that all bodies at the same location above the Earth fall vertically with the same acceleration. If the distance of the fall is small compared to the radius of the Earth, then the acceleration remains essentially constant throughout the descent. So we have this constant acceleration value. This idealized motion is called free fall, and the acceleration of a freely falling body is called the acceleration due to gravity. And therefore, for acceleration, we simply use the symbol g. And that when you see g, it stands for the acceleration due to gravity. Now, this, of course, is the magnitude of it. Magnitude always means the absolute value, or it's a positive number. Now, all that happened here, as you can see, is that the 9.8 meters per second squared, we convert those meters into feet. And we know that if we have 1 meter, that is 3.281 feet. And when I multiply that, then I get the value for G. And this is the value for G in the English units, sometimes called the U.S. customary system units. So if we were to observe what happened in an air-filled tube, if we had two objects of different masses, the heavier mass would fall faster, appear to fall faster. Well, it would fall faster because the lighter object under the influence of air will feel the effects of that air, which could cause it to move from left to right and not necessarily come straight down. But if I have an evacuated tube or a vacuum, in this case, there's no air, then we notice then that the heavier object and the lighter object, every object falls to the earth at the same rate. So that is the acceleration due to gravity, which is 9.8 meters per second every second, which is 9.8 meters per second squared. Now, the important thing to know is this. Acceleration is actually a vector. And in this case, this vector is acting downward. The object is being pulled down. And we just said everything that's acting downward has to have a negative sign. So in the problems, when you use the acceleration vector, when you replace A with the acceleration vector, then it is going to be negative 9.8 meters per second squared. Example 4, a falling stone. A stone is dropped from the top of a tall building after 3 seconds of free fall. What is the displacement y of the stone? So again, we're looking for what is the, not the distance, but the displacement, which is a vector. Therefore, when we solve this problem, this value for y needs to be a negative number. If we solve it correctly, it will be negative. And the reason is because, again, it's pointing downward. Time is a scalar. Time is always positive. Now, what is given in this problem? In this problem, we know the initial velocity because it starts from rest. We know time. We know that the value for A is acceleration due to gravity, and it's negative because it's pointing down. In fact, the displacement, the acceleration vector is always negative. Again, we're not given the final velocity. Therefore, we have to choose the equation that does not require us to know the final velocity. So that's why we choose this equation and put in the variables, and we're able to solve for the displacement vector y. And again, it's negative because we just saw it was pointing down. In this example, let's see what happens when we have an initial velocity that sends the quantity upward. So the referee tosses the coin up with an initial speed of 5 meters per second. In the absence of air, should be in the absence of air resistance. How high does the coin go above the point of release? So what are we looking for? We're looking for y. And in this case, y should be positive. Now again, even though I am shooting the coin upward, it is still under the influence of gravity. So my A, which is due to gravity, is still negative 9.8 meters per second squared. In fact, one reason you know that it's a negative vector that's opposing this motion is because how else would it slow down to boom, it comes to rest momentarily at the highest point. So that tells me that this value of A is negative. Then, of course, we know at the top that the final velocity is 0. And we were given the initial velocity, and the velocity had to put it into motion, was positive 5 meters per second. So in this case, when we solve for the value of y, it will be positive. The next thing I want you to notice here is that we can also use these 3 variables to find out how long is the coin in the air. And we're going to use symmetry for that. But one way to think of it is what goes up must come down. So this is the path that the coin takes to go up. and we know all of the variables, 3 variables, to take it up. So let's use these same 3 variables to find time. And this will be called time up. So my equation says then, that V final equals V initial plus the acceleration. In this case, is going to be due to gravity. And this time will be time up. So once I rearrange this equation to solve for time, and this is, of course, I wrote it specifically as time up. Once I find that time, I simply double that value because the time it takes to go up is the same amount of time it takes to come down. So once I solve for time, that will tell me how long the coin is in the air. First, we solve for the height, the maximum height that it reaches. Plug in those values, we can find that. And then we can also, in the example that I gave here, we can rearrange to find for time. In other words, time up will be V final minus V initial divided by acceleration. Remember, V final is 0 minus V initial. But once we divide this negative by negative, then the time up would be a positive number. Time is always positive. In this conceptual example, it says that there are 3 parts to the motion of the coin. On the way up, the coin has a vector velocity that is directed upward and has decreasing magnitude because it's being acted on by acceleration due to gravity that is acting in the opposite direction, therefore it's slowing it down. At the top of its path, the coin momentarily has 0 velocity, but it's only for a moment. And then what happens? The coin begins to fall again. On the way down, the coin has downward pointing velocity with an increasing magnitude. The magnitude is increasing. It's getting faster and faster, but it's still moving in the negative direction. In the absence of air resistance, does acceleration of the coin, like the velocity, change from one part to another? No. The acceleration vector is a constant. It always acts downward. The magnitude of it is 9.8 meters per second squared, but it's negative because it always acts downward. And that concludes the review of the equations for kinematics in 1 dimension. Please review this as often as you need to get a thorough understanding of the important concepts taught in kinematics in 1 dimension or kinematics along the x-axis.